I want to take a few minutes to cover right now is what I talk about in my version of Unit 4B. Unit 4 is multiple forces. Unit 4B is the energy aspect in multiple forces. Now, in Unit 3B, what we talked about was work. And what I said was work is the net force times the displacement, the distance the object moves. Well, here, net force is parallel with the motion, which means it's either pushing it to move it forward, or pushing it or holding it back. So the force is either with the motion or against the motion. Either one. It doesn't matter. Parallel is an important word. I refer to parallel as a lot in terms of parallel forces, parallel acceleration, all that type of thing. Keep in mind that force is a vector. And the force vector does not have to be parallel. And so what I talk about here in this unit is how do we handle it when the force vector is not parallel. Let's look at a couple of diagrams real quick. Let's say we have a box that's sitting on a level surface, and let's say it gets displaced some distance delta x. In order to displace it, we have to apply force. This force could be in the same direction as delta x, or the force could be in the opposite direction of delta x. Let's say it's sliding already, and this could be a frictional force, and this is some type of a pushing force or a pulling force. This is what I meant by parallel. Both forces are parallel to motion. It could be with it, or it could be completely against it. Now, another situation, same box, it moves, it gets displaced some distance x, but now the force is at an angle. And so the question is, does all the force go into moving the box? And the answer is no, it's not. But keep in mind, this force can be broken up into an x component and into a y component. Didn't give myself much room. Into a y component. The x component is parallel to the motion. So it's this x component, f of x, moves the box delta x. So the work done on the box is that component of the force in the x direction times delta x. Well, if we know this angle, the component in the x direction is just f cosine theta delta x. This is what I was talking about, is what we learned in chapter 3b is the force has to be parallel to the motion. The net force moves the box. This net force is parallel to the motion. That does work. It's still the same thing here, except that we're only looking at a component of the force that is parallel, that does the work on the box. So there's a couple of ways to write the work equation. I think one of the ways on the formula sheet is work is and it has the parallel force times the displacement. It then writes it as f d cosine theta. My preferred way is f cosine theta d, where theta is the angle between the force and the displacement. And that that helps. I like that way because it helps me keep in mind what exactly is the angle, or what theta are we talking about in terms of with this. So keep in mind that the only component of the force that does work that does work is parallel, and this is that key word, parallel to the motion. That's it. The only component. You apply a force to an object as the object is moving, being displaced while that force is being applied. It's only the parallel component of that force that is doing the work. F of x, or whatever. It depends upon the direction of the motion. So this is kind of interesting. Let's look at our picture again. And this is my force. And I've got a component in the x. So the work done on the box is just that component in the x direction times the displacement. There is a y component. Well, if I look at this work, if I said Fyd, this is, remember, it's force times the cosine of theta. So my overall, so that force, my force component in the y direction times the cosine of the angle. This is the cosine of the angle between the force and the displacement. In this case, since the force is up and the displacement is horizontal, the angle is 90 degrees. Cosine of 90 is 0. And so this turns out to be 0. No work is being done by this force in the y direction because it's perpendicular to motion. Perpendicular forces do no work. And that's an important thing. Only parallel component does the work. I misspoke a few minutes ago when I gave you the equations that are on the formula sheet. It's actually delta E, the change in energy, is equal to work, which is a good, I like this relationship because work changes energy. And so the energy level is equal to the work done on the object, which is the parallel force times the displacement Fd cosine theta. So I had this part of the formula. I forgot the delta E, which I think is an important part. Again, this is the parallel component, and I think that's a real important word to understand when things are parallel or when they're perpendicular. So let's look at a couple of relationships between this parallel force and displacement. I'm only looking at the parallel force, the component in the same direction it's moving. If F parallel and D are in the same direction, then theta, the angle between the two, is 0. The cosine of 0 is 1. So work is simply Fd. If the parallel force and the displacement are in opposite directions, something sliding along the floor and there's friction slowing it down, theta is 180 degrees. The cosine of 180 is minus 1. And so now work is negative Fd. Work is not a vector, but we can do positive and we can do negative work. When we do positive work on the body gains energy. Its energy level increases. If we're doing negative work, body loses energy. So its energy level decreases. And these are some important relationships to understand. If we're doing work on an object, its energy level should gain. If an object's energy level increases, and this is something you have to be very careful about, that we get into with conservation of energy. Yes, if you hold something up in the air, it has gravitational potential energy. As it falls, that gravitational potential gets converted to kinetic. Its overall energy level stays the same. But the gravitational potential energy decreases, which means it's losing, something is doing work against that object. The kinetic energy level increases, which means something is doing positive work on the object. You cannot change an energy level without doing work. I'm not talking total energy, we're talking specific energy. And that's something I don't particularly like about this expression, because it's not total energy, it's specific energy, but you got to just kind of keep that in mind. So let's put this all together, and let's look at a problem, and let's look at all the individual forces, and let's kind of see how this might come together. We got a box. It's sliding along a rough surface. It's moving that direction. So let's say we have a force that's pulling it. Let's say we have a frictional force acting on it. Of course, we have gravity, and we have a normal force. And the question gets into the work being done on the box. And here's what you got to be careful about. And I know this sounds kind of stupid, but the source of the force does the work. The question isn't going to be how much work is being done on the box. The question is going to be how much work is being done by a specific force. Because work is Fd cosine theta. It's the specific force. A specific force does work. How much work is this specific force doing on the box? Okay. So, if we're dealing with the pulling force, then the work is Fd cosine theta. F and D are in the same direction, so this just works out to be Fd, and it's a positive value. So the pulling force is doing positive work on the box. The pulling force is putting energy into the box. Great. So let's look at friction. The work done by friction is the frictional force times the displacement times cosine theta. The frictional force is opposite the direction it's going, so the cosine is 180 degrees. The angle is 180 degrees. The cosine of 180 is -1, so this is negative frictional force times displacement. The frictional force is doing negative work on the box. It's taking energy out of the box. Pulling force is putting energy in. Frictional force is taking energy out. The normal force F normal is equal to the normal force D cosine theta. The normal force is perpendicular to the motion. 90 degrees. Cosine of 90 is 0. So the normal force, I wrote Fn. This should be work done by the normal force. This is 0. Because the normal force, and I can't spell normal, because the normal force is perpendicular to the motion. Same thing with gravity. So we have Fg and the normal force are perpendicular to D, to the displacement, so they do no work. This is not always the case. It is the case here because the motion is horizontal. gravity and the normal force are perpendicular to that. And so you gotta have to just keep that in mind. I'm running out of room, but let me go over here and say, now ask, what about the net force? Well, the net work, this is the overall work. The work done by the pulling force, plus the work done by friction, plus the work done by the normal and gravity, which is 0. The net force, if we add these two numbers together, that's equal, or the net work is equal to my net force times B times the cosine of the angle between the net force and D. Now, in this particular case, the cosine is going to be 0, but it doesn't have to be. If I had one of these forces at an angle, the net force might not be at parallel. And so this is what you got to be careful about. Work is not particularly a complicated topic. It's the calculations are relatively straightforward. But you got to be careful because it's not work overall unless they're talking about network. They're going to be talking about specific work, but from a specific force. And that's what you got to be careful about. So this is my unit 5B. It's been a while since I've done this. We've been coronized, and so this is the first chance I've gotten back to do some of these. This is my unit 5. I'm sorry, my unit 4B. I'm getting ahead of myself. Where we're talking about the energy aspects with multiple forces. I hope this has provided some help. Good luck.